work for Math 1452 at Texas Tech University, which is Calculus 2. So in this final video, we'll be doing one final example of work. And in this case, it's going to be about pumping liquid. So let's just go ahead and dive right in. So a tank is shaped like a trough with a triangular base. It is 3 feet high, 6 feet long, and 4 feet wide. It contains water to a depth of 2 feet. And we're asked to find the work required to pump the water to the top of the tank. So again, the work questions are easy to identify because it's explicitly telling us to find work. And we know that it's pumping water because we're pumping the water here. So we are pumping water. So our liquid here is water. So again, like the previous examples, I like to start off by looking at what numbers I see and seeing what they mean. So we have 3, 4, 6, and 2. And these all just give us dimensions of the tank. So 3 feet is the height of the tank. 4 feet is the width of the tank. 6 feet is the length of the tank. And 2 feet is the water level. So I've gone ahead and drawn this out for us here. So one thing that may make this questions like this tough is if you don't know what a trough looks like. In this case, a trough with a triangular base is just going to be a triangular prism. So trough typically means prism. So if it had a rectangular base or a square base, it would be a rectangular prism. So this is what our trough is going to look like. So all of these really just tell us what our scenario looks like. There's no other numbers besides giving us this drawing. But because we know that we're pumping water, if we go back up to our formulas here at this front page, we're now looking here at pumping liquid. So our formula for force, we're going to need weight, density, distance, and the area of a slice. And if you watch that first video, this area of a slice I pointed out is going to be typically the toughest part of this. And then our upper bound for our pumping liquid is going to be the height of the liquid. So we're going to use this information to set up this integral. So our weight density here is not given to us. However, we can recall again from that first page that the weight density of water is 62.4. So again, depending on your instructor, this may be something for you to memorize or it may be something given to you. But in this case, it would have been something we needed to memorize, that the weight density of water, specifically whenever we're dealing with feet, is 62.4. And this is often going to be foot-pounds, I should point out. Okay, so now distance. So the water is going to be pumped out of the tank. So that wasn't something I drew in my sketch, but our water's gonna come out like so. And so I'm just going to say that that water is going to be pumped out vertically somewhere else. So I'm going to say that we're going to use vertical in a vertical orientation. So our variable is going to be y that we're going to use. So again, we can figure out what we want y to represent. And so I'm going to let y represent my current water level. So that means that my y is going to start at 2. My water level starts at 2 and goes down to 0. Okay, so it's going to decrease. My water level decreases as the water is pumped out. And so that's going to help us figure out our distance, and our distance is going to be 3 minus y. So the distance here is the distance that the water remaining for the water to be pumped. So this is going to be similar to our example about a cable. So if you haven't gone back, that one may be easier to watch first. That our distance here was, this 50 minus y, where it was the distance we had left to pull the cable up once we start going. And the exact same thing is going to be true here with pumping water, is that our distance is going to be 3 minus y, and it's going to be the distance remaining for the water to be pumped. So if we're pumping it up, we need to go up to 3 feet. And so we need to figure out, okay, how far up do I need to push this water? So this is going to have a similar feel. There's this inverse operation here, because as water goes out, my water level actually goes down, but I have further to push the water up to get it out. So if this is confusing to you, in my opinion, it really just takes doing repeated examples of these types of word problems to be able to identify when you have that inverse type of relationship. But I think that really drawing a picture and just kind of thinking through, well, as there's less water, my water level goes down, but it has further to go up and out, can be really helpful. So that's going to be my distance. And next I need to find my area of a slice. So again, like we did in the example with the cable, I'm going to put a coordinate grid here. So I'm going to have the point 0, 0 as my base. And then I'm going to try and find a slice. So that's going to be the second picture here, where I have shaded a black slice in my water level. And so this is the slice of water that we're moving. And so you can see that as we get closer to the height of the water, this rectangle is going to get bigger because my trough widens as my triangle opens up as I move up. And if I'm closer to the base of the trough, that rectangle is going to be smaller. So we need to figure out the area of this slice, but this area is going to change. So we can see that by drawing this, my length of my trough is 6, and that's going to remain the same. However, my width of the slice is going to change. And so to find the width of this rectangle, we need to solve for 2x, right? And so I'm just going to, I know that I need to solve for x because I have a 0, 0 down here, and then however far this distance is to this point, well, this point is 0, is x, and then some 0, right? We move over some distance of x on my x-axis, and so that's going to be, I'm going to put it in red, this distance here, and then I actually have 2 of those, right? So I have a second one on the other side, so I'm going to need to solve for 2x. So my width of my slice is going to be 2x. So my area here is going to be 6 times 2x, right? My length times my width. However, we know things in terms of y, right? So we've decided that we're going to use y as our variable. So we need to figure out what x is equal to. So we can do that by looking back here at our coordinate grid. We have our point 0, 0, and then we know that our trough here has a height of 3, and it has a total width of 4. So here in the back, we're breaking up that width into halves, right? Because this coordinate plane splits that width in half. So really we have a distance of 2 here and a distance of 3 here, which makes that point that we have drawn there 2, 3. So we can think about what's the equation of this line. And just remembering that slope is rise over run, we go up 3 and over 2. So we have this line has the equation y equals 3 over 2x. And so we can use that equation to go ahead and solve for x. So we have that y equals 3 over 2x. And if we multiply both sides by 2 over 3, we have that 2 over 3y equals x, and then we need 2x, so we just multiply both sides by 2. So that gives us the equation 4 over 3y equals 2x. So we can actually rewrite our area of a slice to get 24 over 3y, which is 8y. And so now we're working in the same variable. So with this process, you may have questions such as, well, why couldn't I just have decided that my my distance was going to be in terms of X and not deal with this? Well, that's because our water is being pumped vertically out of the tank. So we actually are forced to deal with Y because our water is going either draining out of the tank in a vertical manner. So this is the reason that we have to use Y. The width of our tank isn't being affected by the water coming out, because the water level, as the water gets pumped out of the tank, the water level is going to change, and that's measured by a vertical distance, that water level. Okay, so this is the area of a slice. So you may need to watch this a few times. This is a very complicated example to try and wrap your head around. So if you need to watch this a few times, please do. But once we have our area of a slice, a distance, and our weight density, that is going to set up our integrand. So our force is going to be our weight density times our distance times our area of a slice, which was 8y. And so I'm going to pull out the 62.4 and the 8 to give me 499.2. And then I'm going to have a 3 minus y and a y. And I'm going to simplify that one more time to be 499.2, 3y minus y squared. Okay, so that's going to be my force, which is going to become my integrand. And next, identifying our bounds. Since our water level is 2 feet, our lower bound's 0 and our upper bound's 2, because that is the water level. That's how much water we need to point out, so we can pump from 0 to 2, getting the water, all of the water that's currently in the tank. And now that we've identified these things, we set up our integral. So we're going to integrate from 0 to 2 of 499.2 3y minus y squared dy. And I'm going to go ahead and pull out that coefficient of 499.2 and then integrate this. So I'm not going to spend time to actually integrate this like I did in the previous videos. I'm just going to tell you this for practice on your own, that this is going to be 1497.33, and we need to make sure to include our units. So this is joules. So like I said, really the toughest part of this question was finding the area of our slice. And so we just need to make a slice in whatever liquid we're pumping, see what my length and width are for my slice, see what changes, and then use whatever information we have to find a relationship or a dependency there to describe the area. So that is going to be it for this example, and this is the final example on this worksheet on work. But with all these examples, we hope that this helps you work out some of your work word problems. So good luck.